Good afternoon. So this is our 719 Mathematical Economics. And we continue our study of dynamic programming. So let me share my screen. Okay, so let's open a new page. All right. Okay, so let's minimize that. So up to this point, we looked at guess and verify, right? Guess and verify. Then we looked at value function iteration, then policy function iteration. So these two specifically are projection based. Okay. Then there is also this thing called perturbation methods. Okay. So you can check a paper by Schmidt, Grohe, and Uribe. I think it is 2004 Journal of Economic Dynamics and Control. Okay, so that's one of the main references. So the idea is this. So once we have, so suppose that we have this problem, right? So there's this state, then there is a reward function that also depends on state and control, right? So we have state t plus 1, okay? So basically we are choosing the control variable, and then we have the transition equation, okay? And we also have some initial values, all right? So again, as you know, so this problem could be with multiple control variables and multiple state variables. It doesn't really change anything. So that could be a vector valued function or a real valued function. So it doesn't really matter. So out of this, at the end, we try to find solutions in this form, right? So control variables will be depending on the state variables, okay? So these are called policy functions. Similarly, of course, this will be directly following from this, right? So here I have st plus 1 f st c st. Okay. So the idea of perturbation method is basically this. So we want to find at the end a function of control and state variables. Okay, and as you know, so after first order conditions and envelope conditions, right, I basically find a vector of control like variables and state like variables. Okay, so this f function then, so what is the dimension? So suppose that this has dimension n, right? And this has dimension m. So these are, so there's an n vector of control variables and m vector of state variables. So at the end, this system must have n plus m equations, all right? So if you want to understand this in the context of the optimal growth problem, remember that you have kt, then you have uct beta vkt plus 1, right? So you have the constraint plus that, right? So first here you have the first order condition with respect to c. So this is just one equation, right? Beta v prime kt plus 1 minus 1 equals 0, let's say. Then you have the envelope condition. Okay, your envelope condition is V prime KT equals beta V prime KT plus 1 F prime KT, right? And then you have the constraint as well. So you have basically three equations. As you know, you can replace V prime KT with, say, lambda T. Then you have two control-like variables, right? Lambda T and CT, and one state variable. So these are your controls, and this is your state. And then you have three equations, 1, 2, 3. Okay, so these 1, 2, 3 are in your F. So in this particular example, you have n equals 2, m equals 1. All right. Now the idea is to approximate. So if you have, let's say, control-like variables and state-like variables, then you first imagine a steady state. All right. So obviously you're going to use these functions to find the steady state. Then you want to approximate CST, okay, around S. All right. So that's the main idea of the perturbation method. And at the end, of course, you know your policy function is something like this, right? Your policy function is a function of the state vector, and then you have the transition equation. Okay. So the transition equation is basically F ST CST. All right. Of course, these are, let's say these are the correct functions that you not know. With a linear approximation, you can do a linear approximation. I mean, I will not explain how you solve the system. So there are some algorithms, such as Blanchard-Kahn algorithm. So I'm not going to go into that detail. Okay, you can find it in the Uribe paper. But if you have a linear approximation, basically you're going to have a function such as this one. All right, so H will be a matrix. And similarly, you're going to have a function like this. Okay, so again, G will be a matrix. All right. The beautiful, so this is sometimes called the state space form. Okay, if you look at the paper, you're gonna find some details. You can also imagine a quadratic approximation. So instead of taking the Taylor approximation of F at the first order, you can take it as the second order. Then you will have something like this. You're going to have, let's say, H1. Oh, by the way, sorry, I have a mistake here. So let me re-explain. So this will be, like this. Forget about this. So let me show you once again. So you will have in the first order approximation, you will have something like this. So CT deviated from the steady state will be H times ST deviating from the steady state, and ST plus 1 deviating from the steady state will be like this. Okay, and obviously these H and G are matrices. Okay, in a second order approximation, obviously you will have something like this, right? First you have the H1, ST S bar, then you have H2, ST S bar squared. And here for the transition equation, you will have, let's say, G1 ST S bar plus G2 ST S bar squared. Okay, and you can also take higher order approximations. All right, so you can also take higher order approximations. Again, I will not show you, since we don't have time, I will not show you the exact details of the Blanchard-Kahn algorithm or any other algorithm, but this is a perturbation method that obviously you want to realize this. So in the case of, let's say, value function iteration, remember, for all the state space, we approximate the value function, right? But the perturbation method approximates the solution around the steady state. So for some reason, if you want to do some sort of analysis away from the steady state, then it becomes inaccurate. All right. So for perturbation method to work, if you want to use perturbation method to solve the dynamic programming problem, then depending on the research question you have, you must be close to the steady state. Once you move away from the steady state, your algorithm becomes inaccurate. So that's the negative side of it. The positive side of it is that it is very fast. I mean, comparatively much faster than the projection-based methods, because in the projection-based methods, you calculate value function for any point in the state space. Here, you are basically solving matrix equations. So these matrices, H, G, etc., they will be unknowns, and given the parameter values of the model, you're going to find H and G matrices that solve the problem. Okay? So solving matrix equations is definitely easier than calculating the value function for each point in the state space. Okay? So in the stochastic version, there will be additional shocks around, so I will show you that as well. But now let me give you a couple further examples of deterministic problems. Okay, so one problem would be a monopoly problem. Okay, so let's imagine a problem of a monopoly. Okay, so the firm want to maximize this. Okay, so this monopoly firm, it has some discount factor, all right? I is the interest rate here, and there's a profit, okay? So the profit, of course, depends on what? Profit depends on price times the demand. Now, we want to put this variable into the demand function, all right? And there's this marginal cost, theta. And again, this is output, okay? So I will explain what xt is. So theta is the marginal cost or the average cost. They're the same here. So this is greater than 0. Now demand is like this. Okay, so demand function is like, let's say, this with beta positive. All right. Now xt here is a demand shifter, right? If xt is larger, for any given price, the demand is larger. If xt is lower for any price, demand is lower, right? So if you draw it, you have, let's say, Q here and P here. So you have something like this, all right? So this is your X, okay? Sorry, this is your X. Okay. So it's a demand shifter, right? If X is increasing, demand curve shifts to the right. Now, how XT moves, that's the idea, okay? Now, suppose that there is this dynamic of this XT term, all right? So what does it tell you? Here we have, let's say, rho between 0 and 1, and phi and gamma greater than 0, okay? So what's going on here? First, there is some persistence in this demand shifter, all right? Then larger price has a secondary effect on the next period, right? So if the consumer faces a price that is larger, then some sort of behavioral shift occurs in the demand function. All right, you may imagine that this is behavior, or this is consumers' preferences that depend on psychologically, that depend on the price that they observe in the previous period. So there could be many reasons why would that work with phi positive. So higher price today decreases the consumer's orientation to this particular commodity in the next period. All right. So now this is of course different than the static problem, right? Because in the static problem, you have what? You have the profit. Let's say this is a static problem. In the static problem, you have the profit, and profit is like this, right? So P times X beta P minus theta X beta P. So if you solve this problem, you find some P static, right? So you can do it. But then in the dynamic programming version, you will have something different, right? Because now the monopoly firm will consider the current pricing decision, the effect of the current pricing decision on future demand. Okay. So you will have this minus theta xt beta pt plus you have the continuation value, right? And continuation value will depend on X. Obviously, you are choosing price, and this is subject to xt plus 1 equals gamma rho xt minus phi pt, right? So P is your control, X is your state. So for the control, you have the derivative. So it is what? Minus 2 beta P, right? Minus, plus theta P, theta beta P, right? So no, there's no PT here, I'm sorry. Right, so I'm taking the derivative with respect to P. I have X, right? I have X minus 2 beta PT. Then I have plus theta beta plus the derivative of this with respect to xt. Then the xt's derivative with respect to price, it is phi, all right? Now, suppose that price is positive. Then you also have the envelope condition. In the envelope condition, you have what? Price here minus the marginal cost, right? Then 1 over 1 plus I v prime xt plus 1. Then you are taking derivative with respect to x, it is equal to rho, right? Now, if you compare the price in the case of static profit with the price originating from this equation, you will understand that they differ. And now the the monopolist considers the pricing decision in such a way that the continuation value will be optimal, right? So this part will be optimal. So the choice of price today, remember the constraint, right? So here is your constraint. So the choice of price today affects the demand function tomorrow, and the monopolist considers, takes this into account by charging the price, when charging the price. Okay, so I will leave the rest to you. So work on this, show that this is different than the pricing originating from this function. All right, so compare these two pricing decisions and try to find the steady state. Work on the problem and try to understand the dynamics of this. Obviously, you will have a system, right? When you change V prime theta, let's say with lambda t plus 1, then you will have a system of these variables. So that system will be what? Linear, I guess, here, right? Yeah, it looks like it will be linear. So then you can analyze the steady state, uniqueness, stability, right? All of the stuff. Now, my second example will be, so another example is a firm problem, so an investment problem. So we actually studied the continuous time version of this, okay? But here you will see the discrete time version. So again, the firm wants to maximize the market value. So the market value is, so from some initial point to positive infinity, let's write everything in real terms. So there's that. Okay, so R is positive. Now profit depends on that, and there is some payment to the labor, and then there is some investment expenditure. So the capital stock then changes in this way, right? So here W is positive, and delta is the depreciation rate that is between 0 and 1. Sorry, so K0 is positive, right? So the control variables are, N and I, and state is basically K, right? So how do you attack this problem? Well, very simple. Write the Bellman equation. K is your state. Then you have the profit. So profit is FKT NT minus WNT plus IT. Then you have the continuation value. All right. So obviously you are choosing labor demand and investment expenditure. Sorry, this will be a minus, obviously. Okay. So for N, you have what? You have Fn KT and T minus W equals 0. For investment, you have -1. Don't forget the constraint. Constraint is like this. IT delta KT, right? So you have -1. And then plus beta V prime KT plus 1. Then you want to take the derivative of KT plus 1 with respect to IT, okay? Now here, let's suppose that there is some minimum and maximum levels of investment. Okay, remember we made a similar assumption in Takayama's example. So then you have the envelope condition, right, for the state. So you have V prime KT equals FK KT and T plus beta V prime KT plus 1 and the derivative of KT plus 1 with respect to KT, right? So you have something like this. So this will be, oops, what's going on? So this will be equal to what? This will be equal to 1, right? And this will be equal to what? 1 minus delta, right? Oh, wait, sorry. So this is not beta here. Sorry. So this is, remember, 1 over 1 plus r, okay? And this one is also 1 over 1 plus r, all right? You must be careful with these things. So anyhow, the choice of labor is static, right? So there's no appearance of the value function's derivative here. But then the choice of investment, of course, is a dynamic choice. Why? Because your investment today increases your capital stock tomorrow, right? So once again, you have a dynamical system. You may want to, okay. So you may want to find the steady state and then study the properties of the steady state. Okay. I'm gonna just show you that. Just a sec. Sorry about this. Okay. So you have, again, if you replace this with some, I don't know, lambda, your system will be like, let me open a new page. So first, you have minus 1 plus 1 over 1 plus r lambda t plus 1 equals 0, right? Something like this, I guess. Yes. And then you have lambda t equals fk kt and t plus 1 over 1 plus r 1 minus delta, right? You also have kt plus 1 equals it minus it plus 1 minus delta kt. And you have fn kt and t equals w. Okay. So you can write some steady state conditions. Eventually, you're going to realize in a steady state with positive investment, you will have something like this. So lambda star, so let me write this. So lambda star will be equal to 1 plus r, so it will be a constant. Then lambda star will be equal to so I am forgetting some lambda here, right? So there is lambda t plus 1 here. So I guess at the end you're gonna find this. So you should confirm these results. So kn star plus 1 minus delta. Then you have Fn k star n star equals W, and then you have I star equals delta k star. Okay. So again, the transition dynamics will be very simple. Why? Because the continuation value will be constant. All right. The derivative, the shadow price of capital stock will be constant. All right. So that simplifies all the stuff, but you must be careful with the so if you eliminate lambda, for instance, you're gonna have something like this. Check that. So in the second step, you're gonna have Fk k star n star equals R plus delta. Fn k star n star equals W, right? So this becomes the cost that the firm pays for capital. All right, any questions about these, all these things? Now we have 3 minutes before the break. And looking over my examples, I don't want to get lost, of course, within all these sheets. Any questions in the meantime? Okay. So I have one further example, but I think we will not have time for this. Maybe I can post this online so you can work on this. All right. For now, I have to stop and we have to work on the stochastic dynamic programming problems. All right. So any questions before the break? So basically, I gave you. Oh, there's one last example. Sorry. Okay. After the break, I will show you this. There's one last example I want to discuss. A deterministic problem. All right. Then so it is around 1:40 here. So let's meet at 1:55 after the conversion, of course. Then we're gonna continue. All right. Okay. 1:55. 1:55. All right. Bye-bye.